Okay, hi everyone, this is Ehab. Welcome to CS 143 first actual lecture. So today's agenda we are going to talk about time complexity. We are going to dive through into big O, big omega, theta, and you are going to do the worksheet. Then we are going to talk about best and average, worst complexities, and you are going to do a worksheet for that also. So let's just start with no introductions. Okay, so space and time complexity. Time complexity is commonly estimated by counting the number of elementary operations performed by an algorithm. What do I mean by elementary operations? By what the CPU is executing. And usually those take a fixed amount of time to perform. Thus, the amount of time taken and the number of elementary operations performed by the algorithm differ from one machine to one machine, or from one algorithm to algorithm, by a constant factor. So we have something else. It's called space complexity. We are not going to talk a lot about space complexity. I'm going to kind of talk about it briefly, summarize it, and you don't go with the hassle of a space complexity. So space complexity is a measure of the amount of working storage in algorithms. So basically we're talking about memory consumption. So we're talking about the storage needed by the algorithm. So that means how much memory. So in the worst case, we want to know how much memory that algorithm needs. So as with time complexity, we are mostly concerned about with how the space needs grow. So in big O terms, as the size n of the input problem grows. We are going to see what that means exactly. So we are going to talk about big O notations in terms of n. So most of our data structures will have a space complexity of n. That is if we have a list of people and we are processing this list. Then we need a space for each element we are going to store in this list. This is simple. This is something you have seen in CS141, in Java 1. So if there are 10 people, then we need 10 spots in memory, assuming that every person needs one spot to be stored in memory. So as the number of people n grows, so do the spots in memory we use. So the time complexity, however, of an algorithm is commonly expressed using the big O notation, which excludes coefficients and the lower order terms. And you're going to see those today a lot because we have a lot of examples to show you. How do we exclude coefficients and why? The most important thing is why. So big O is an upper bound for the number of operations based on the input size. I'm going to talk a lot on big O and what does it mean and how we are going to express that and all these things before I give you the formal definition. Because I'm concerned of what your understanding of big O notation will be after this lecture. So what is big O notation? Think about it. After what you have heard, we have n terms, and if we have 10 people, 10 spots, if it's complexity, space complexity, if it's time complexity, the time needed to process every element in my list. So what is big O notation? So with big O notation, we express the runtime in terms of how quickly it grows relative to the input. And usually the input, we express that in terms of n. As the input gets arbitrarily large. Okay, so big O is basically the upper limit of the growth rate of the number of basic operations, the runtime, as the input size to an algorithm grows arbitrarily large. So where input size is the number of items being processed or searched. Now, whether you search, whether you sort, whether you do anything to that list, we are going to say processed. The list is being processed. So it is used to place algorithms in general categories of performance, such as we have a constant runtime, we have logarithmic runtime, or logarithmic complexity, linear, quadratic, and so on. So here's a big O complexity in terms of the graphs they represent. So the big O of 1, it's going to be constant. It's actually covered by big O of log n, because big O of log n is going to be kind of next to the constant. Then we have big O of n. Then we have a bigger complexity of big O of n log n. Then big O of n square. Big O of 2 to the power n. Then n factorial, and so on. So in terms of numbers, to show you how different is each algorithm, and if we have big complexity, how that is going to affect my time based on the input I have. So let's take this. If the input is small, like 1, I'm processing just 1 person information. If it's constant algorithm doing that, then I'd take 1 second. If it's logarithmic, it's going to take 1 second also, near that. If that is quadratic, then it's taking 1. Cubic, 1 second. But it's 2 to the power n, and being 1, then it's 2 seconds. Because we need a lot of processing. Okay, what if we have 32 people? So if it's 1, if it's big O of 1 algorithm, it takes big O of 1. Why was that? Because we are saying, okay, it's constant. 32 is constant, right? Then big O of log n, big O of log, so that is log 32 to the base 2, then that is 5. That is 5 seconds. What if that being big O of 2n? This is 2. Then it takes more than 4 billion seconds. Okay, this is in terms of numbers. Okay, so what is a typical or reasonable problem size we can solve for a given exponential time bound? If you know that modern computer will perform roughly 2 to the 30 power, to 2 to the power 30 operations per second in 1 second. Then if I give you a context to that, if the operations were 2 to the power 30, then we have 1 second. 2 to the power 48, that takes 3 days. This is the number of operations we have. Our algorithm is executing. So if we have 2 to the power 54, then you would need more than 6 months for this algorithm to finish. This is why it's important to say if it's logarithmic, if it's constant, linear, and so on. So we have something else. So we said the big O notation, this big O is the upper bound. What is this? This is big omega. Big omega is the lower limit, the lower bound, the lower limit of the growth rate of the number of basic operations, which the number of basic operations, I'm talking about runtime. The runtime. As the input size to an algorithm grow arbitrarily large. So the input size is the number of items being processed. Remember that? So usually we have big O and big omega. And if both are equal, we are going to call that theta. So as we said, we can have big O, constant big O, and constant big omega, logarithmic big O and logarithmic big omega, linear big O, linear big omega, and so on. So the theta is when both are equal, the big O and big omega. So if this is big O and this is big omega, this, where they meet, where they cross, is the big theta. The big theta. Okay, so how quickly the runtime grows? We have some external factors that affect the time it takes for a function or an algorithm to run, like the speed of the processor. It doesn't make any sense to say that my i7 2.5 gigahertz CPU is going to work on your algorithm exactly as someone else's machine with i3 and 1.8 gigahertz, because my machine is stronger. Also, even if my machine is strong, what else is running on that machine? And many other things. So it's hard to make a strong statement about what is the exact runtime of an algorithm. Actually, when I run my algorithms on my machine, on the same machine, depending on what's running on that machine at different times, that would give me different runtimes. For example, that would take the same exact algorithm with the same exact input, sometimes 2 seconds. And sometimes if I'm running Photoshop, that would take, for example, 6 seconds. This is different, even though I'm using the same machine. And this proves that. So instead of trying to make a strong statement, we use a big O notation to express how quickly its runtime grows. Big O notation is satisfactory situation or satisfactory notation that gives me rough idea of what I expect from my algorithm. Okay, so relative to the input, since we are not looking at the exact number, we need something to phrase our runtime growth in terms of. This is where we chose the big O notation, because if I have a big O notation of n, then I'd say it's on the order of the size of the input of n. If I have n square, then in the order of the square of the size of the input. Not just the size of the input. Now the square or the cube and so on. So as the input gets arbitrarily large, our algorithm may have steps that seem expensive when n is small, but are eclipsed eventually when the n gets huge. So for a big O analysis, we care most about the stuff that grows fast as the input grows, because everything else is eventually eclipsed as n gets very huge. So, as you can see, this is going the first term, or the biggest term, not the first, the biggest term is going to determine what our equation or what our shape of the algorithm is going to look like. So as n grows, this part will grow much more rapidly than other parts. So I will give you an example. If n equal 2. So this is 2 times 2 times 2 times 2, which is being 16. This is 2 times 2 times 2, then this is 8. This is 4. This is 4. So as you can see, this is going to grow fast, because when you make that 3, this becomes 64 compared to the 16 when n was 4. This becomes 3 times 3 times 3, which is 27 compared to the 8. This being 9 compared to the 4. So this gives you always the biggest gap when you transition from one n to another. N equal 2 to n equal 3 to n equal 4. So we're almost always interested in this one. So as n grows, here's the proof to that. As n grows, n square, n to the power 4 will start to dominate. This is starting to dominate. Look, here is some inputs. N equal 1, n equal 2, n equal 3. When n equal 12, for example, or n equal 14, you can see this term is here. This term is here. But this term, the a times n to the power 4, is here, which is almost always going to be near the total of that. So this is making a huge difference in our equation. So, in other words, I can say Big O notation states a claim about the greatest amount of some resource. Usually we talk about time, sometimes we talk about space, that is required by an algorithm for some class of inputs of size n. Typically, we are talking about the worst such input, the average of all possible inputs, or the best such input. So if you know what an asymptote is, you might see the why behind Big O analysis is sometimes called asymptotic analysis. So the term asymptotic means approaching a value or a curve. Here it is. Approaching the value or the curve arbitrarily closely as some sort of limit is taken. So a linear or curve that is asymptotic to a given curve is called the asymptote of. This is the asymptote. You can see it's close to that curve. This asymptote line is close to that line in that curve. So asymptotic analysis refers to computing the running time of any operation in a mathematical units of computation. Also, the asymptotic analysis is input bound. If there is no input to the algorithm, it's concluded to work in a constant time. Other than the input, all other factors are considered constant because it's asymptotic, right? So if and only if, this is the formal definition. The formal definition. And actually, to be honest, I'm not interested in on you remembering or memorizing the formal definition. I'm always interested in you understanding what that means. Or if I give you an example of an algorithm, you analyze that and tell me this algorithm is big O of what? Big omega of what? And so on. This is what you're going to do actually in the complexity sheet. So the formal definition says if and only if there is a positive constant m, such that for all sufficiently large values of x, you can sometimes see people using n. The absolute value of fx is at most m multiplied by the absolute value of g of x. That is, f of x equal big O of g of x if and only if there exists a positive real number m, this is the factor, and the real number x0 such that f of the absolute value of f of x less than or equal to m multiplied by the absolute value of g of x for all x greater than or equal x0. We are going to explain that thoroughly today. So in a typical usage, the formal definition of big O notation is not used directly. Rather, it's the big O notation for a function f is derived by the following simplification rules. And those are simple. If f of x is a sum of several terms, you ignore anything but the largest growth rate. So you keep the largest growth rate and ignore anything else. Anything else is being omitted. If f of x is a product of several factors, any constant factor is omitted. Okay. So for example, if we have f of x 6 times x to the power 4 minus 2 x cubed plus 5. So using those two rules, I'm going to solve that and deduce the big O notation of this formula. So the first thing I see, is it a sum of several terms? Yes, it is. Here is one term, the other, and the third. So yes, it's sum of 3 terms. The 6 times x to the power 4 and minus 2x cubed and the 5. So what we said is we are going to keep the greatest, which is this one. This is the greatest, and we are going to omit those. So we don't want this one, we don't want this one, just keep this one. Okay, we kept this one. Now, is there any factors? Any constant factors? Yes, we have. We have 6. This 6, we don't want it. So, we now have only this after we omit the 6 from the 6x raised to the power 4. Now we can say f of x is big O of x raised to the power 4. So mathematically, we write f of x equal big O of x raised to the 4th power. Now, this is if I have a function. We can say if I have a function. What if I give you an algorithm? I say, okay, did you use the function from this algorithm? Then find the big O. So first you should find the equation, then find the big O. Okay, here is one operation. We have a for loop. If we have a for loop, then things go in terms of n usually. So we have operation, 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 operation. Okay, that's good. But now, how many times each operation would be executed? Okay, this is executed once. Once I visit that, I don't visit that again. This is also the initialization to the for loop, as you know, from CS141, from Java 1, from Java Basics. It's executed only once. This is going to be checked n times. For every round, you're going to check that. This is going to be incremented every time, the I. So we have n operations in here, n operations in here. The body, whatever the body is, it's going to be executed in operations, right? Then we have one operation here, one operation here. And by the way, if we have embedded for loop, the body of the embedded for loop is going to be executed n square. If we have 3 embedded for loops, the body is going to be executed n cube. Here it's executed only n because this goes n rounds. So after all this, we have 1, 1, 1, 1. So we have the result of 4. We have 3 n's. We have 3 n. So total is 3n plus 4. Here is my f of n, right? In terms of x, f of x equals 3x plus 4. And here is the chart for that. You are not required to draw charts as long as you get me this. Then the next step is, what is the big O notation of this for equation you came up with? So, okay, let's do it. Do we have multiple terms? Yes, we have. Okay, take the biggest one and ignore the rest. So this is the one I want, and I would ignore this. Then, I have this. Do I have constant factors? Yes, I do. I have 3. So ignore the 3, omit that, then what you have left is big O of n. You have n, then you have big O of n. Now I taught you how to get the big O of n, but now you must ask yourself, does it make any sense? Does it make any sense to have this big O of n? Because clearly, if big O is the upper bound, 3n plus 4 is greater than n. I guarantee you that. If n is 1, then this is 3 plus 4 equal 7. This is greater than 1. Right? So, does it make any sense to say that? Let's see. So, keep in mind that the big O is the upper bound. How could that be the upper bound? Remember the formal definition? I asked you not to memorize it, but I also asked you to understand it. To have a better understanding of the formal definition of big O, let's take a look at this. Let's break it down. I intentionally delayed the breakdown of the formal definition up to this slide. With an example, you understand better always. So remember, big O has extra components. It's not the n. It has also x of 0 and n. So x of 0 is the point at which the big O is greater than the function, as x approaches infinitely. So m is the positive coefficient that we multiply big O by. So if I'm going to apply those two to my big O of n, having the equation 3n plus 4. So if I have m is 4, x0 is 5, as you can see, x0 is the 5 in here. This is where the big O, this orange line, is going to keep going above the blue line, which is my equation, my 3n plus 4. So if I have m is 4, so for all inputs, any input above 5, above the x0, this is true. For n greater than 3n plus 4. This is true. So when I say I have big O of n, I mean I have m multiplied by that, m being 4. And the lowest n is x0, which is the 5. Okay. So here is also, that is being a bigger chart, and you understand that we still refer to it as big O of n because we have m, such as 4, that makes it always greater the actual equation we have as long as it passes x0. So the tightest bound is preferred. What do I mean by that? Remember that we have this f of n. We have 3n plus 4. I can also say big O of n4 is greater than 3n plus 4. And this is going to be true. Because if you have 1 and 1, then this is going to be, for finding the x0, 1 and 1. That gives you 1 for this, and 1, that gives you 3 plus 4, 7 for this. You keep going until you find n square starting to give you better, or not better, greater output than the 3n plus 4. Starting with n5, 3 times 5, we have 15 plus 4 equal, assuming we chose x0, 5. This is 19. It's just the n square, even if m equal 1. Just the n square gives you 25. So yes, big O of n square is always bigger than that. As long as you have n greater than x0, which is the 5. Right? Okay. Do we prefer to say we have big O of n square? No. Because we can find n, big O of n, with a certain m and a certain x0, which is going to be tighter than big O of n square. As you can see, the gap in here is very big, very huge actually, compared to this gap. Approaches infinity, right? So this is all about big O of n. Now let's just talk a little bit about big omega, which is lower bounds. The lower bound of an algorithm is denoted by the big omega, the symbol big omega, right? And this is pronounced big omega. Or some people just keep saying omega for simplicity, because they want to differentiate between the big notation of the big O and big omega. You just say omega. for that. So the actual definition, the formal definition of the big omega is similar to the definition of big O. For every t of n non-negatively valued function, t of n is in set, and we're going to use the n. If you have big O of n and you have big omega of n, you're going to start to saying in big omega of n, in big O of n. Because the exact thing you don't say in, you don't see that wiggle room, is only in the theta. So, going back to explaining what is big omega, t of n is in set big omega of gn if there exists two positive constants c and n0 such that t of n is greater than this amount, c times g of n, for all n greater than n0. So it's very similar to the big O notation, except that is looking for the lower bound. So to show you how you can find from your equation, from the same exact equation, how you can find the big O notation versus the big omega notations, let's do this. For the big O, we said if we have multiple terms, we get rid of the lowest or the smallest term. So we end up with this term, right? C2n squared, then we get rid of the C2, and we know that it's n squared. Another way to do it is we are going to find the highest or the biggest term and take that power and apply it to the other terms. So we are going to say, okay, we are going to make this in terms of n squared. Here it is, C2n squared plus C1n. We are going to make that n squared. So we can say that C2n squared plus C1n is less than or equal this, C2n squared plus C1n squared, which is less than or equal to this, right? Equal to this. So now we can say this is true for all n greater than 1. So that leaves us with big O notation of n squared, with C being C2 plus C1 and n equal 1. Right? Okay, so we applied this on the upper bound. Which basically gives us the same thing if we drop this and get rid of the C2. Gives us big O notation of n squared. How are we going to do that with the big omega? With the big omega, lower bound, we are going to first determine the highest term, as we do with big O notation. And now we can say, by getting rid of this, we can say for C2, for C equals C2, this equation is big omega of n squared with C equals C2 and n equal 1. With n equal 1. So the theta notation is when both the big O and big omega gives us the same description of, in terms of n, like n squared, like n cubed. So how do we form that in a definition? The definition is when the upper and the lower bounds are the same within a constant factor, we indicate this by using big theta notation. So an algorithm is said to be big theta of h of n if it's in, remember that we use in with big O, in with big omega, and we didn't say in big theta, because we just say big theta, to be big theta, if it's in big omega of h of n. As I said, we dropped the word in for the big notation of big theta. So this function gives you also big theta of what? Of n squared. Why is that? Because the big omega of it was n squared, and the big O of it was big O of n squared. Now, the only change is within the factor. This factor is C2 plus C1. This factor is C2. So the only change is the factor. And this is exactly what we were saying. If it's only the factor, then we say they're equal, and this is big theta of n squared, and this n squared. Okay. So the theta notation provides the strongest statement we can make about an algorithm, because it pretty much gives you the exact thing, pretty much. So in sequential search algorithm, it's big O of n, big omega of n, within or in big O of n, within or in big omega of n, in the average case. So we can definitely say it's big theta. It is, I didn't say in, it is big theta of n in the average case. So the big theta analysis is always preferred. For many algorithms, it's easy to come up with the equation that defines the runtime behavior. The analysis that is most commonly used in algorithm is well understood if we have a big theta analysis, a big theta, because then we found the point that we can say the big theta, the big omega and the big O are equal. So common orders for the growth seen often in complexity analysis: big O of 1 being set as a constant, big O of log n, logarithmic, big O of n log n. We say n log n, even though the logarithm is involved. Big O of n is linear, big O of n squared, quadratic, cubic, polynomial if it's big n, big O of n, 2 to the power, big O of n, exponential, and so on. So those are going to be in your test. I may give you a question in your test that says, arrange these terms, arrange these notations. I say n to the power n, and factorial, and so on. Here is that. I'm going to give you the link on Canvas. I'm going to give you the link I get this photo from. It's going to give you a list of algorithms like this, but it's going to be nicer with some colors. This is going to give you the kind of algorithm or example of that algorithm, and what it's being called, what is the running time, and I'm going to, at the end of this quarter, we are going to try to analyze our algorithms in terms of big O. So asymptotic notation can be thought of as relational operators, right? For functions similar to the corresponding relational operators for values. So we can say, okay, if they're equal, then it's big theta. If it's less than or equal, it's big O. If it's greater than or equal, it's big omega. What is being equal? What is being less than or equal? What is being your equation? Okay, there is a common misconception or common mistake. Some people confuse the upper and lower bounds with the best and worst cases. It's like you're confusing hamster to ham. So the best and worst cases relating to a specific runs. A best case search is when you find the data you're trying to find or the element you're trying to find at the beginning or the first element in your array. The worst case search is when you didn't find the element you're trying to find in your array, or you found it at the very last, the last element. So there is a big misconception sometimes with people trying to understand worst, best, average cases with big O and big omega. So remember that how we found this. We said this is one operation, n operations, because it's being checked every round, it's being incremented every round, or almost every round. This is being executed every round. This is outside the for loop, so it's happening once. This is happening once. So we have this equation and we found the big O notation of that. This is how we did it, how we found the big notation. So now pause the video, and go to Canvas. I'm going to show you your Canvas. Here is your Canvas. Go to Canvas, go to lecture 2, Here is the slides, you can find them here. Go do these complexity. This is a complexity worksheet. You can download that complexity. I'm downloading that complexity worksheet. Open that. And you're going to find those questions. Here is an algorithm. Try to provide the equation in here and write the equation, write the big O of this equation. Now you would say, okay, how would I do that? I would say, okay, when you go there, you can submit an assignment. Click on submit assignment, then you will get a text entry. For example, for this one, I would say 1A, 1B. 1A, then I would write my equation, f of x equal blah, 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 whatever that equation is. Let's assume that equation is 3n plus 4. Then I would say B, this is big O of n. This is big O of n. Then 2A and B and so on. And so on. So, this is not yours. Okay. Now, this is the worksheet. This is the worksheet that you're going to do when I explain best, worst, and average cases next. So do that. You pause the video. You have done this. Submit your assignment. Then go back to the video. Play the video, because I'm going to continue explaining the best, worst, and average cases. And here is the link I told you about. Here it is. See that? And those are saying, okay, if you're going to operations on arrays, on hash tables, sorting algorithms, what are the complexity, best, average, worst complexity of those, and so on. So let's go back to our lecture. So now you have done this complexity, best, average, and worst complexity. Best, average, and worst complexity. So sometimes we talk about the big O in terms of the worst case scenario, the average case scenario, and the best case scenario. So in computer science, we need those for an algorithm to express what the resource usage is, at least, at most, and on average. Now, whether this resource is the computer cycle, CPU consumption, or the space, memory consumption. So usually the resource is being run times in case of time consumption. Time consumption meaning the time complexity. And some other cases would be the memory consumption. Okay, so usually we would find those because the development and the choice of algorithms is rarely based on the best case scenario. We want the average case scenario and the worst case scenario, because you want to convince your client, you want to convince your boss that your algorithm is good. Your boss wants a good algorithm. It doesn't make any sense to manipulate the data, because you want your algorithm to find the first element. You should try to calculate the runtime when it's being found at the first element, then in the middle, and at the end. Like the best case scenario is finding, if I'm searching an array for number 2, then the best case scenario is to find it at the very beginning. I just did one round and okay, I found it. This is a constant complexity. It's almost nothing, right? But for the worst case scenario, I'm going to find that worst case scenario in terms of the big O notation. This is why we started big O notation, because it measures the resources, whether it's running time or memory, this algorithm, your algorithm, requires in the worst case. So it gives the upper bound of the consumption. So in case of running time, worst case time complexity indicates the longest time your algorithm would take based on the size of input n. Thus, this is guarantees that the algorithm finishes on time. So the order of growth of worst case complexity for your algorithm is used to compare efficiency of your algorithm to others. Your algorithm to another person algorithm doing exactly the same thing. Two algorithms doing the same thing. Finding an element in an array. So it's typically impossible to determine the exact worst case scenario. So I'm not going to ask you to find the exact worst case scenario. This is why we use the big O notation, because we want to find if it's not the worst case, then as bad as the worst case. I'm going to give you an example of that. So the worst case scenario might be, if I'm looking for an element in an array, is to visit every element and not finding that element, the element I want, the element I'm searching for. So the worst case scenario might be if the element does not exist in the array. But something as bad as the worst, because it's going to be near the worst, might be having the element I'm searching for as the last element in my array. So the worst case scenario might be finding that element at the very last, which took me n processes, right? N processes. So I did this, I visited this. If I have, for example, 9 elements like this, I visit 1, I visit this, I visit this, compare that to 3. Visit this compared to 3. Visit this compared to 3. Visit this, blah, 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 up to this point. Visit this compared to 3, then I have done n operations. Right? If I didn't find it, I also have done n operations. Even if I didn't find it. Okay, so the motivation for studying worst case complexity, because sometimes real-time requirements need upper bounds upon their worst case execution requirements. Actually, when you work for a company, most people would ask you for average and worst cases. Average and worst cases. And many people would be interested in the worst case. In the worst case. Because it doesn't make any sense to give me the average case and say, okay, here is my complexity. My algorithm would finish if the element I'm searching for, the elements I'm trying to sort, they're going to be finishing in 2 seconds. But I would guarantee that you're saying the right thing. Then I run it, and in my case, the thing I'm trying to find, the thing I'm trying to sort, the thing I'm trying to do was at the very end, and that used multiples of the 2 seconds you said. Doesn't make any sense. So, for example, task scheduling may need to guarantee a process complete less than a given time. It's like I'm going to tell my customer that I can find your whatever the person you are trying to look at and to look for in the data in less than 4 days. Then it should be 4 days, because the worst case is going to be 4 days, or roughly 4 days, near the 4 days. It may be less concerned with the average case, right? Because it doesn't make any sense to say, oh, I'll find it in 2 days. Then that takes me 4 days. Okay. So in computational complexity theory, the average case complexity of an algorithm is the amount of some computational resource used by algorithm averaged over all possible inputs. Trying to find it at the very beginning and trying to find it at the very end. It's like you're doing, if I have n elements, I would find it almost near this place. Right? In the middle. So the analysis of such algorithm leads to the related notions of an expected complexities. And this is what we just said in terms of the average case, right? In terms of the average case. This is where we summarize the whole big O notation, big omega. So the big O notation expresses the runtime in terms of how quickly it grows relative to the input as the input gets arbitrarily large. So beyond this point, I have 2 slides. I'm not going to ask you about those 2 slides in the test, but it's always good to know that there are 3 primary motivations for studying average case complexity. First, although some problems may be interactable in the worst case, the inputs which elicit this behavior may rarely occur in practice on the worst case. So I would go find it in the average case. Because I may not encounter the worst case. So I would need the next best thing. Or the not the best next thing, the next worst thing, which is something near the average. I'm not going to fool myself and always report my best case to say, oh, I'm very good. This is me fooling myself, not fooling others. So second, average case complexity analysis provides tools and techniques to generate hard instances of problems which can be utilized in areas such as cryptography and sometimes in de-randomization. If you study cryptography and security, you may see these scenarios where you want to study the average case complexity more than the worst case complexity, and sometimes more than the best case. Third, average case complexity allows discriminating the most efficient algorithm in practice among algorithms. Sometimes you want to do that because it's going to be equivalent to the base case complexity, like the quicksort. some applications that would make is that for problems we want to solve, this is a good thing. We can hope that the particular instances we care about are average, not worst, and remember that we are not reporting the best usually, because we don't want to fool ourselves and fool others by saying I have the best case scenario. Usually what I do is I'm going to report the worst, but if I know that I rarely could see the worst, then I would say, okay, here is the worst, but note, my algorithm usually works beside or around the average. Okay, we're done with our lecture today. And don't forget to go to your Canvas and do these things. Do the two complexity sheets. And if you have any quizzes or anything. So the answers to those two worksheets are going to be published automatically at this time. Why at this time? Because if you go to your two complexity worksheets, you're going to find them due on April 60th at 11:59 p.m. April 60th, 11:59 p.m. This is because I'm teaching in the spring of 2020. And this is being recorded in the spring of 2020. Have a good one, and see you in next lecture, or talking to you in next lecture.